Hey everybody, I'm Dortz, and this is the C++ tutorial on arrays and searching. So, in here, I'm going to cover the basics of big O notation, arrays, pseudorandom numbers, sorting algorithms, and searching algorithms. And I also got to apologize for my sound. It seems like I've moved my recording studio to a cave. But, so, for this tutorial I included a few more libraries: time, stdlib, standard library, and conio, which is console IO. And time in the standard library is what we need for random numbers and the time function, which we'll get to when we cover pseudorandom. And with conio we need getch, and that's for only if you're running under a GUI. This is going to keep that window from immediately closing, so you just add it at the end before you dump out of main. All it does is it waits for keyboard input of any kind. So, first, big O notation. For algorithms, it's designed to actually tell us about how fast an algorithm is going to run, but generically big O is used to find a function that's always going to be bigger. So like if we have f of x is x times c, and c is guaranteed to be less than x, our obvious big O is x squared. So in algorithms, it's going to be the maximum and average time for a specific algorithm to run. Now we aren't going to measure algorithm times in seconds because no computer is the same and everything's going to run at different speeds. Instead, the effectiveness of an algorithm is measured by how many times it needs to run, or compare values. So usually that's in a standard of n, which is the amount of data being sorted, or for our purposes, the size of the array. And so if it's big O n, it's running in big O n time. So the algorithm's going to do n comparisons before it finishes. So, perspective. N squared, very inefficient. It's going to take n comparisons, and it's going to run through all of those comparisons n minus 1 times. Like a while loop running, and each time it runs, it's going to do n times. So n log n is taking log n runs and n comparisons. N is just going straight through the array, comparing each value. And I'll get to arrays in a minute. And log n is going to cut it in half until you have only one value. Now we're going to see just these four numbers when I do big O, and these will just be the definition of the worst case or average case for all of the algorithms I'm going to show. So, obviously there's other parts to algorithms. It's swapping time usually is going to be a factor. I mean, in modern computers, it's basically free time. Theoretically, it is, but, you know, again, modern computers, it's going to do like no time with swapping. It's going to be a small constant. So we can just about ignore it for most, except in cases where we can't. So, like with EEPROM or flash memory, that's going to take an insane amount of time to run even efficient algorithms here like quicksort. So I have a sort that I'm going to show you that solves that swapping problem. So I'm going to jump right into the explanation of what I'm going to show you. First, bubble sort. It's a bad algorithm, but, well, it's used to introduce sorting because it's very simple to understand. So it's going to take element 1, and then take element 2, compare them, and then swap them if necessary. So the worst case is going to be where it's going to take n squared comparisons and swaps, which, like I said before, is bad. Selection sort fixes that swapping issue. It's still going to do n squared comparisons, but the worst case is only big O n. And that's very good for if you have problems with swap speeds. And update of selection sort is cocktail sort, which I'm not showing, but it's basically the same thing except it grabs a max and a min. Funny thing here, it ends up taking the same amount of time because it's just doing double the comparisons and double the swaps for each run of the algorithm. Quicksort. General, it's basically the best simple sort you can do. It's fast, elegant, implemented with simple arrays. Bubble sort generally takes n squared time, and so does quicksort. And that's only in the worst case. But for the best case, it's going to run in n log n time. And it's really actually easy to hit this specific value. And I'm going to actually show you how to get near that time and even be able to beat it. But I'm not going to go over that until the show notes. But the key element with quicksort is the recursive step. So back when I was first learning this, my professor described recursion basically like a bunch of desk clerks. Each one does a little bit of the work and then passes the rest of it off to another SAP to finish it. So in practice, recursion is basically a function that has to call itself with modified parameters. So in the specific example of quicksort, the work of one clerk is just going to take a pivot point, which I'm selecting right at the head. It's not very efficient, but the partition function that you might write would be very efficient at this because this is the key for it. It's going to take that pivot point and then compare all the values in the array that clerk gets, and then split the array in two and hand the rest of the array off. So one clerk passes it off to two other clerks. One clerk has the lower end of the values, one clerk has the higher end of the values. And they actually have half the actual workload, and they sort their parts, break it in, and send it off. And so it'll keep doing this until they get down to one value and can't pass it away. And then the algorithm's going to kick out. So when you think about it, it's going to guarantee that the array is going to be sorted because the last set of clerks are only going to get one number and they can't pass it along. They have nothing to sort, therefore they can guarantee that their array is sorted because it's only one element long. So, on the two searching algorithms we're going to show, linear search, straightforward brute force search. It's going to take big O n time, where it's just at the end of the array that it's searching for, or like when it doesn't find anything. So the next is far more elegant, called binary search. I wrote in two implementations, but I'm only going to use the second, a recursive definition of it. And remember before I called these overloaded, and this is different types and different parameters. So, main function. First thing we see, an array of 1,000 elements. Yay, an array. It's the simplest of all the data structures. It just makes a list of n elements. So I'm only going to be using integer-based elements, but again, with the type, you can do just about anything. So when I'm declaring it exactly like this, it's going to build it into what's called stack memory. For any purpose that you have for it, it's memory managed by the system. But if I was going to dynamically allocate it, I would do this, where I'm declaring a new pointer x and assigning a new integer array of size. And that's going to be the runtime specific size. It can be user defined or whatever. And this is of course assuming size is an integer. The memory access like this is going to be put into heap memory. That's the same memory, like I said before, that's used by pointers. Or maybe I didn't say it before. But it's dynamically allocated pointers will set up into heap memory like that. So again, essentially the same thing, because even up here, ARR is used as a pointer to the array. So if we saw up here, when we're passing the array, we use these brackets. We could pass it by reference, but then we'd only be passing the first element of the array. Here, it's telling the compiler to know that there is a full array attached to the pointer we're sending it. The same thing happens when we're deleting, too. If we dynamically allocate our array, then we are in control of the memory that it holds. So if we print x, like the dereference x, it's going to print the first element of the array, same way as the pointer. Whereas if we delete x, it's going to delete the head of the array, and it's still going to keep the rest of it allocated, which is a problem because that's going to be just a major memory leak, because we can't release any of that. So we have to delete, tell it it's an array x. Not enough of that. We're also going to use a copy of the array for continuity purposes. Make sure that we have the same composition for each sort to demonstrate how fast they run. So, pseudo-random numbers. Not really random, pseudo-random. They are based off of a set algorithm, but for our needs, decently random set of numbers is fine. Here we have to use a seed, which is like a starting point for the algorithm, and the way we do that is usually with the system time, and for other purposes like cryptography it is absolute shit, but when we just need a chunk of data, this is perfect. Now srand, set random number generator, or seed random number generator, unsigned time. Now this time 0 is going to go to time, and this function returns an integer. And we want this integer cast as unsigned, because it'll return negative or positive, just it's going to overload by the system time because it's a number of seconds since some time in the past. And this is going to unsign that, so it's going to be from 0 to 65,000 something. And then it's going to get that number into srand. And it's going to take that number and it'll give us our seed. Now if I wasn't going to seed this, every time I called rand, it would set the default seed and I'd get the exact same number of the exact same set of random numbers each time. And that's, well, basically useless. So here we have how we're going to fill our array. Referencing array is very simple. We use the name of the array, bracket, index number of the value that we want to access, close bracket. Now the indexes for arrays start at 0 and go to 1 minus the size of the array. Here we have 1,000. This is going to run from 0 to 999 and then kick out. Can't access 1,000, that's the termination character for the array. So, it's going to take every element of the array, grab a random number, modulus 51. And that's from 0 to 999. So, what is modulus? If I didn't describe it before, it's that percent sign, and it's the remainder of. So 3 modulus 2 is 1, 51 modulus 51 is 0, 80 modulus 51 is 29. So our random number modulus 51 is going to give us a set of numbers from 0 to 51 and fill each number into one element of our 1,000 element array. So first thing we do before we run off, we're going to copy the array, and then each time we run a sort, we recopy it. But